In today's lesson, we're going to learn about the complex conjugate, which sounds really fancy. It turns out it's fairly simple, but it's a really powerful tool that we have in working with complex numbers. Let's go ahead and take a deep breath. And let's begin. So, as I kind of alluded to just a moment ago, it turns out that the complex conjugate is really important in our study of complex numbers. I also mentioned that it's pretty straightforward. So as far as a definition is concerned, suppose that you have a complex number x plus iy, sort of our general rectangular form. The complex conjugate of that is x minus iy. So all you're really doing is changing the sign of the imaginary part. The way that we notate this is there's sort of two different ways to notate it. You either do a z with sort of like a star asterisk or a star exponent, or you just put a bar over the top of the z. Those are two different ways that you can sort of indicate that you're doing a complex conjugate. There's one other definition. I don't use this one nearly as often, but it's still a good one. And that's the definition of a conjugate pair. And so the idea here is just that if you take a complex number and its conjugate, those are conjugates of each other, and together you refer to them as a conjugate pair. So the rest of this video is going to be devoted to sort of working with these things and using them and seeing what sorts of properties these complex conjugates or these conjugate pairs have. I should also mention that because the complex conjugate is fairly simple, I'm also going to be using this lesson as an opportunity, or maybe an excuse, to go through the conjecture proof process. So before we do that, I want us to do these two examples that are going to be really similar. And as we're doing these examples, I do want you to sort of be paying attention to any similarity that you might see between the two problems and the answers that you get, because it's going to lead into the next thing that we do. So in this first example, here's what the first complex number z is, 3 minus 4i. You're asked to find z star, which is the conjugate, and then compute the product of those two things. Compute the product of the conjugate pair. So first of all, what is z star? What is the conjugate? Hopefully this is really straightforward for you. This is just 3 plus 4i. All we have to do is change the sign of the imaginary part. So if this had been plus, we change it to minus, but since it was minus, we change it to plus. The next thing you're asked to do in this problem is compute the product. Compute z times z star. Now this is just complex multiplication, so pause the video, make sure that you can do this on your own. So when I do this, I'm going to do 3 minus 4i times 3 plus 4i. And what we get here is 3 times 3, which is 9, 3 times 4i, which is plus 12i, negative 4i plus 3, which is minus 12i, and finally negative 4i times 4i, which is negative 16i squared. You'll notice the imaginary parts drop out. We know that the I squared turns into negative 1, and that'll multiply with the negative 16 already to give me 9 plus 16, and so I get 25. So 25 is z times the conjugate of z. Now, it's hard to ask at this point if you notice anything, because, like, what's there to notice? We did math. Often when we want to notice something or write a conjecture, we need to do similar problems multiple times and look for similarities. So we're going to do another problem very similar, another complex number, find its conjugate, and then compute the product and see what we see. So go ahead and pause the video and work through this one on your own. So the conjugate w star is going to be negative 2 minus I root 3. For the product, I'll do the original complex number times its conjugate. And so when we do this, oops, I just realized I put a square root right there. This should just be a 2. There we go. Negative 2 times negative 2 is 4. This times this is plus 2i root 3. This times this is minus 2i root 3. And finally, this times this is negative I squared. And then root 3 times root 3 is times 3. As we've seen before, this I squared becomes negative 1, which is going to cancel that. These imaginary parts drop out, and I just get 4 plus 3, which is 7. Now, because we're in the same room, I can't hear your answers to this, but I'd encourage you to sort of think and maybe even say out loud yourself or to write down, what do you notice that's similar? Like what stands out to you? What do you notice that happened in both of these? There's a couple things that you might have noticed. One of them is that it was almost like these two things We're setting up for the factoring of like a difference of squares. That might have been one thing. Another one you might have noticed is that the imaginary parts canceled out in both of them. And what that sort of means is it means that both times when we multiplied together a complex number and its conjugate, the answer that we got for both of them was something real. You might have noticed something else. If you want to, feel free to sort of write that down on the side and put a question mark next to it. I'll try and comment on your notes when I'm going through them. The thing that I really want to hone in on today, though, in this first conjecture, is about the realness of the answer. So I know this might be a little bit scary, but I'd encourage you to pause the video and write down how you think you would write that as a conjecture. And a conjecture, by the way, is just a statement of something that we think that we see that we want to try and prove. So you want to try and make it mathematical. It should be precise, but the language isn't magical. So try and write sort of a mathematically sound conjecture about what you feel like you saw. So we could use the vocabulary conjugate pair. We could say the product of a conjugate pair is always real. You could also have written something like, given a complex number z, the product z star will be real. If you wrote down something different and you would like input from me on whether or not your conjecture was sort of the same thing or acceptable, circle it, put a question mark next to it, and again, I'll try and make a comment as I'm going through and checking these later. So now let's get to the proof. Hopefully you remember when we were learning about proofs of trigonometric identities that we usually like to start our proof with some sort of introduction. We may want to start with some definitions. We also want to sort of give the person that's reading our proof a sense of where we're going and how we're going to try and do this. So what we'll do here is let's start with a let statement. Let's start with let z equal x plus iy for x and y being real numbers. And I know that we pretty much always assume that x and y are real numbers, but when we're doing a proof, we really want to be precise. So we're going to tell everybody, hey, z is going to be x plus iy, x and y need to be real numbers. Now, we may not be ready to write our introduction yet, but our hope, our method here is going to be that we're going to now multiply z by its conjugate and hope that the thing that we get out is real and that we can show that it's real. And so you can even write that. You could write this and say, we hope to show that this is real. Now, I'd actually encourage you to sort of try and finish this proof on your own. Could you come up with an expression for what this is, and then at the end, write a statement about why that thing is always real? Well, let's see here. If z is x plus iy, then z star is x minus iy. Okay, so now if we multiply this out, x times x is x squared. X times negative iy is minus x y I. Iy times x is plus x y I. I can change the order because, multiplication is commutative. And when I do this last one, minus I squared y squared. Okay. Now, we know that the I squared is going to turn into negative 1, and that combined with this negative is going to make it positive. These two things are going to drop out because it's, you're adding and subtracting the same thing. So what we wind up with here is x squared plus y squared. And at this point, in my opinion, we're not done. You really want to write a conclusion. You want to write a sentence about what you've just shown, right? And so you might write something like, because x and y were both real, x squared plus y squared must also be real. Therefore, we have shown that the product of any complex number and its conjugate will always be real. I mean, I don't know about you, but this is exciting. Being able to prove things is something that's, I don't know, I mean, it's a TOK question of whether or not it's, unique to mathematics. But so much of math is really about proving things and knowing that things follow from other things and that what we get is reliable. So there's another vocabulary term that I want to teach you here, and it's related to proof, and it's the idea of a corollary. And a corollary is you may have just proven something and then notice something else along the way. So a corollary is sort of like It's like a statement that comes after another conjecture that you've just proven, or comes after a theorem that follows closely from it. And the corollary that I want to sort of get to is this x squared plus y squared. I feel like we've kind of seen that before. Isn't the modulus of z, isn't that supposed to be the square root of x squared plus y squared? So wouldn't that mean that the modulus squared is x squared plus y squared? So there's sort of this corollary that, whoa, wait a minute. Doesn't that mean then that the modulus squared is equal to z times z star? And you can see how this corollary, it kind of doesn't even need any proof. You can see that we got from here to here, and we remember this relationship, so I don't really need to prove any more work here. This work, this thing, effectively follows from the proof that we did up above. Now, just because something is a corollary and it sort of like follows quickly and easily doesn't mean it's not important. In fact, this corollary is really, really, really important, and we're going to come to it and we're going to use it a little bit later. Now, I want to give you an opportunity to do one more of these little mini proofs on your own, and this one should be really simple compared to the last one. I'm giving you the conjecture this time, z plus z star, so the sum of a complex conjugate pair is real for any complex number x plus iy, with x and y being real numbers. So I'd encourage you now to try and write a proof for this, similar to the one that we just did. All right, so just like we did before, I'm going to go ahead and write down this let statement again. So let z equal x plus iy for x and y being real numbers. Okay, we're now going to consider, and you can even use the word consider z plus z star. The consider word, by the way, isn't super important. It's just a nice way to sort of introduce what's happening next. So consider z plus z star. This would be x plus iy plus x minus iy. We can very clearly see here that the imaginary parts are going to drop out, and what we're left with is 2x. And at this point, we again could write a really brief statement about what has happened and what we found. So what I wrote here, since x is real, 2x is clearly real, which is what we wanted to prove. This structure of which is what we wanted to prove is a really common sort of conclusion sentence that I'll use in a proof. So especially if I didn't give an introduction, I'll get down to the end and say, hey, by the way, that's what we wanted to prove. By the way, I want to mention the word clearly. Clearly you want to take care with. If your work wasn't clear, don't say clearly. But if you've shown all of your work and if you've been really careful about that, clearly is a really good word to use. There's actually room here for another corollary. It's not as important, but I wanted to sort of give you guys a chance for that. So do you see anything that this 2x is? Like, can you think of any corollary that you could write here? One thing that you could write is you could write that z plus z star is, if you think of what x was basically the real part of z. And what we just found is that when you add a complex number together with its conjugate, you wind up with 2 times the real part of z. And again, you can sort of see here that there really isn't any need for a proof here. This is something that follows from the work that was done previously. So we've spent a lot of this video talking so far about what the complex conjugate is and how we can prove results with it and things that we know about it. I'd really like to put one of those to use now by updating our process for division. Okay, we learned a method in I think actually our first lesson about complex numbers for how to divide complex numbers, but it was kind of clunky. It took a lot of work, and so I want to update that now. So key point: we can quickly divide two complex numbers by multiplying the top and bottom of the fraction by the complex conjugate of the denominator. Right? And you're going to see here in just a minute how the work that we just did with our first proof sort of works along with this. So suppose that you're given a problem, 2 minus 3i divided by 1 plus 5i. If you would like to do this and express it as a single complex number, you can take the division that you are given and multiply the top and the bottom of this thing by the conjugate of the denominator. So the conjugate of that denominator is 1 minus 5i, because I'm just supposed to change the sign of the imaginary part. I need to multiply that to the top and the bottom, so that I'm effectively multiplying by a really fancy 1 over here. Now, what do you expect is going to happen down here in the denominator? Anytime we multiply a complex number by its conjugate, what do we get? We get a real number, which is great, right? So working through this, in the numerator, I'm going to have 2 minus 10i minus 3i plus 15i squared. And in the denominator, I'm going to have 1 minus 5i plus 5i minus 25i squared. So now we can go through and simplify these. In the numerator, this I squared turns into negative 1, which is going to make this symbol right here a minus symbol. So in the numerator, 2 minus 15 is negative 13, and then minus 13i, that's kind of neat. In the denominator, let's see here, the I squared is again going to turn into negative 1, which will make this positive. The imaginaries are going to drop out, and I'll wind up with 26. And then because they wanted it in this form, we can actually split this thing into two separate fractions. Negative 13/26 minus 13/26 I. And those actually can both be reduced to a half. So negative a half minus a half I. Right? So again, I don't know that this is quick, but it doesn't require the setup of some equation and breaking that into two equations. This we'd really like to use as sort of our standard method for dividing two complex numbers now. Next in this lesson, I'd like to talk about the geometric interpretation of the complex conjugate. So what does this mean for Argand diagrams? And so this key point here, the complex conjugate of a complex number is its reflection in the real axis. And this shouldn't be super surprising. If you had x plus iy, it would be, like x in this direction and y in this direction. And so there's that complex number. Here it is, x plus iy. If the conjugate is supposed to be x minus iy, it means you're going to go over the same x, but now you'll go down the same negative y, and you'll get this point down here, which, as you can see, is sort of the reflection across the x-axis. I'm sorry, not the x-axis, the real axis. Now, as a corollary to this, right? As a corollary, if we thought about this in polar form and said that z was r cis theta, it means that this angle right here is theta, and this length right here is r. Well, then it would make sense that the conjugate would be the exact same length. It's just that the angle instead would be negative theta, right? So we could write this as r cis negative theta. So what this sort of means is anytime you see a negative angle inside of one of these things, there's space for you to potentially think of it as the conjugate of the same thing with a positive angle. That's something we're going to come back to several lessons down the line. For now, I'm just going to sort of lay it out and leave it here. I have one more sort of group of information for you, and then the rest of the video is just going to be examples. There are several properties of the complex conjugate, and many of them are very, very intuitive. Note, I'm not going to use these extensively now, but they may be useful in proofs and things that we're going to do down the line. So I wanted them to be here and make a quick mention of them. All of these things here, by the way, are things that can be proven. They're things that you guys can go through and that you can prove. We may actually have some exercises with that later. This just says if you add two complex numbers together and then take the conjugate, it's the same as if you did the conjugate and then added or subtracted them. If you do the conjugate of a product, then that's the same as doing the product of the conjugates. If you do the conjugate of a quotient, then that's the same as the quotient of the conjugates. And the same thing here, the conjugate of a power is the same thing as the power of the conjugate. So they're all very intuitive sorts of things. I wanted to make mention of them here. And again, if you were asked to prove this, what you would really do is you would simply say, you would do let z be x plus iy and w be a plus bi, And then you would do this side using these things. You would do this side using these things, and you would show that those two sides are, that the left-hand side is equal to the right-hand side. So the video is getting kind of long, so I don't want to go through the proof of any of these. I think we've done enough proof work. I want to get to some other examples now. So I have 3 examples prepared of sort of different problems and different things that we can work through, all that are going to somehow use this idea of the conjugate. So the first one, they're giving us z as something expressed in polar form, and we're being asked to write z over z star in terms of r and theta, simplifying as much as possible. Okay. So what I'm going to want to do here is I'm going to want to write this thing in terms of r and theta. And the cis notation is good, but if I'm going to be doing algebra with it, I really want to sort of expand it out. So z on the top is going to be r cosine theta plus I sine theta. Yay. Now in the denominator, the conjugate would just be this thing, but with a minus in between. So r cosine theta minus I sine theta. Now, some of you might have thought from a few minutes ago that z star is also supposed to be cis of negative theta, or r cis of negative theta. I could have used that here, but having a different angle inside of these things isn't super helpful for me. If I'm going to do this algebra and multiply some things around, I would rather have it expressed like this where the angles are the same. Now I've got some good news here. It looks like the top and bottom both have a factor of r, so I'm going to cancel those things out. I hope that nobody's trying to cancel out the cosines. You can't do that because cosine isn't a factor of the top. Cosine is a part of a factor, so I can't cancel those. But I'm thinking, when we've got one complex number divided by another, one of the strategies we learned is to multiply top and bottom by the conjugate of this thing down here, right? So if I multiply top and bottom by that conjugate, let's see here. So I have cosine theta plus I sine theta over cosine theta minus I sine theta. The conjugate of the bottom is cosine theta plus I sine theta. And I would do that for the top and the bottom. Okay, so in the numerator, this is going to be a lot of stuff up here. In the numerator, I'm going to have cosine squared theta, that's cosine times cosine, and then I'm going to have plus, let's see here, plus this times this. So I cosine theta sine theta, and then there's another one of these, so plus I cosine theta sine theta, and then finally the last terms plus I squared sine squared theta. This is all divided by, now in the denominator, because we pick these things as conjugates, we sort of expect the middle terms to drop out. So I'm going to get cosine squared theta, let's see here, minus, I guess it would be plus I cosine theta sine theta, and then minus I cosine theta sine theta. So we're not surprised, those cancel out just like we anticipated, and then minus I squared sine squared theta. Whew. Okay, now let's look for some good news here. I squared is -1, which will make this a minus. Down here, I squared is -1, which will make this plus. So in the numerator, my real parts are cosine squared theta minus sine squared theta, and my imaginary parts are cosine, well, it's actually just two of the same thing, isn't it? This is 2I cosine theta sine theta. And in the denominator, I have cosine squared theta plus sine squared theta. Now, depending on how well you remember your trig identities, there's some amazing stuff that happens right here. This thing right here, this is the identity for cosine 2 theta. And over here, 2 cosine theta sine theta, that's actually the identity for sine 2 theta. And in the denominator, cosine squared plus sine squared, that's actually 1. And so this thing that we just found, cosine 2 theta plus I sine 2 theta, this is basically cis 2 theta. And that's our answer. What this just showed is that if you take z and divide it by z star, you're going to get cis of 2 theta. You're basically going to get double the angle with a modulus of 1. In these last two examples, I want to talk about solving equations that use the complex conjugate. And I want to remind you guys and let you know, sometimes it's going to be easier to solve equations by using the method that we had before of writing z as a plus bi and then just solving a system of equations, one of them that's real and one that's imaginary. And other times it might actually be easier to use the properties of the conjugate and solve for z directly. And that's what I'm going to try and do here. So in this problem, you're given that the magnitude of z, or the modulus of z, is the square root of 6. So as soon as somebody tells me that, I start thinking, wait a minute, modulus squared is going to be 6, so that means if I ever have z star, that's going to be 6. That's just sort of like useful information to keep in mind in problems like this. So now this equation here, I see a z star in the denominator, and I could sort of do like fraction busting. If I multiplied this whole problem through by z star, I'd cancel it out here. Over here, I'd get z star, which I know what it is, and then I could just deal with this stuff on the right. So let's see what happens when I do that. If I multiply this whole thing through by z star, I'm going to get z star on the left. In the middle, the z star is going to cancel with the z star, giving me minus 10i. And then that z star does still need to go to the 6. So I'll have 6z star. Okay? Now, right here, I can see that z star is supposed to be 6. So now I have 6 minus 10i equals 6z star. Now, I want to solve for z, so let's just divide by 6. If I divide everything in the problem by 6, I'm going to get 1 minus 5/3 I is z star. And that means we can tell what z is, can't we? Doesn't that mean z is 1 plus 5/3 I? And at this long in the video, you may be surprised that we can actually get through an example in only 2 minutes. I really wanted to sort of show you here, even at the end of the video, that lots of times using these properties of the complex conjugate can make getting through a problem a lot faster. Unfortunately, working with properties of the complex conjugate isn't always the way to go. Sometimes we're going to need to refer to our old method, and so I wanted to do an example of that as well. In this one, if we let z be x plus iy, so now just like we've done before, I'm going to take this z and I'm going to just sort of put it into this, right? So I'll have x plus iy plus 4 times x minus iy, and this will need to be equal to 2i. Okay. And just like I did before solving these things, I'm just going to break this into real parts and imaginary parts. If you'd like to pause the video and do it on your own, go for it. X plus iy plus 4x minus 4iy equals 2i. So now let's look at real parts. Real parts here would be x plus 4x, and there isn't a real part over here, so equals 0. So x plus 4x equals 0. I mean, that's awesome. That means x has to be 0. And then for the imaginary part, I've got iy, positive iy, minus 4iy equals 2i. So we can drop the i's out of this. Negative 3y equals 2. So y has to be negative 2/3. And so it says find all solutions. So my solution is supposed to be z. Z is negative 2/3 I. And that's all I have to tell you today about the complex conjugate. I really hope all that made sense. If you have questions, please make sure that you ask them. I'm more than happy to talk further about this stuff. And as always, best of luck with your work.